also called as asymmetric carbon. We are given with 4 options, and the meaning of this is a chiral carbon atom is a carbon atom which is attached to 4 different groups. It can be 4 different atoms or it can be 4 different groups. So if you consider that, let's write the structure first so that we'll be able to make out which is the correct answer. 2-butanol, so 4 carbon atoms, and at the second position you have OH, and everywhere you have, I'm just balancing the valences. So if you see this carbon is attached to 4 different groups. This is OH is different from H, which is different from CH3, which is different from CH to CH3. So this is chiral. And let me go to the second one. That's 2,3 dibromobutpentane. Pentane in the sense there are 5 carbon atoms and there are bromines at 2 and 3rd position. So let me satisfy the valency. So if you take this carbon is attached to 4 different groups. Even this carbon is also attached to 4 different groups. So this is a chiral carbon and the chiral molecule. If you take the 3-bromopentane, before completing the structure itself, you can tell here this group which is attached to this carbon and this group which is attached to this carbon are similar. So this is not the chiral center. This carbon doesn't contain any chiral center. So our answer is option 3, but still we can go for the next one too. 2-hydroxypropanoic acid. So one is COH at the first center, and here you have OH and H and CH3. So at the second carbon, it is again a chiral center. So the correct answer would be option C, which has similar groups on both the sides, which is not a chiral one, which is a symmetric carbon. The second question which we have here is amines and the peptides. Peptide is a linkage that is present in the proteins. These can be separated by. So what are the options available? Let's see. Differential extraction, distillation, paper chromatography, and none of this. Usually the option none of this rarely comes as answer if you observe the previous papers. And then if that is the case, then differential extraction is done when you have the compound which has to be separated and you're going to take 2 immiscible liquids. When you take 2 immiscible liquids, you can do the extraction, which is not possible in case of amines and the peptides. The distillation, if you take the next one, distillation, there should be a boiling point difference, large boiling point difference between the 2 substances which you take. But if you take the amine series, the first amine and the second amine, they differ by a small molar mass. That's why their boiling point doesn't vary too much. So you can't go for the distillation as well. The one which is remaining here is the paper chromatography. The paper chromatography refers to you have a paper and it is kept in a solvent and you are going to mark the substance which you are going to separate, and here there is a solvent which is a mobile phase, and the pores of this paper are the stationary phase. So based on their ability to climb into the paper, the substances can be separated. So the correct option would be option A, that's amines and the peptides can be separated using the paper chromatography. So let's move on to the third question then. Here, the most suitable method of separation of 1:1 mixture of ortho and para nitrophenols is. So just by looking at the option, you can say sublimation can't be the answer, because sublimation refers to any substance which directly goes from solid to gaseous state. So that's not possible in case of ortho and para nitrophenol. So you can't do that. In the chromatography, refers since they have the similar properties, the ortho and the para nitrophenols, you can't even separate them by the chromatography. So what you are going to do? We'll see the structure so that we get the answers well. It is orthonitrophenol. If you are going to draw the structure, this is phenol and this is the ortho position. And this is a phenol and nitro is in the ortho meta para position. If you see the structure here, there is a hydrogen bonding inside the molecule. So this is called as intramolecular hydrogen bonding. Intra refers to there is a hydrogen bonding inside the molecule. But if you take the next compound, the OH and the NO2 groups are away, so they can't form the hydrogen bonding inside the same molecule, but that is going to form the hydrogen bonding with the next molecule. So here you can observe the intermolecular hydrogen bonding. So there will be difference in the boiling point, and also here if you consider the intra and the intermolecular hydrogen bonding compounds, this is going to form the association with the other molecules, because of which this will have the lower boiling point and this is going to have the higher boiling point. Now what happens is when you do the steam distillation, this is non-volatile, non-steam volatile, whereas this is steam volatile. So this is vaporized and this can be obtained first, whereas the non-volatile substance is left behind. So the correct option will be option D. So our next question is, which of the following pairs shows the functional group isomerism? So first of all, we have to see what exactly is functional group isomerism. So isomerism refers to the compounds have the same formula. And the functional group isomerism in the sense, they should have the different functional groups. So when you say the different functional groups, we'll see the functional groups which are given in the compounds. So here the first one, alcohol and the amine. Alcohol is OH and the amine is NH2. They can't have the same general formula or the same formula, because OH, here you have oxygen, here you have NH2. So this can't show any functional group isomerism. And if you see the carboxylic acid, this is COOH and this is CHO. So here there are two oxygens and here there is only one oxygen. So this also can't show the functional group isomerism. So we are left with the aldehyde and the alcohol. So if you take aldehyde, that's CHO. If you take alcohol, that's OH. Still, this contains carbon. This functional group contains a carbon, but this functional group doesn't contain the carbon. So even this is not possible. We are left with alcohol and ether. For example, you can take this compound CH3CH2OH, and the next one is we are going to arrange this way. Here OH is alcohol and this is ether. You can see their formula. That's C2H6O here, and this is also C2H6O. So they have the same formula, but the functional group is different. So the correct answer would be option D. Let's move to the next question. How many isomers of C3H9N compound have the amine group? So one is clear, there should be an amine group. So if there is amine group, we'll arrange the carbon atoms first, C3. And let me attach in here the valency, the number of bonds for nitrogen is NH2. So this is one possibility. And we are going to satisfy the valency. And let me check whether the formula matches with the structure. Totally number of hydrogens would be 3 to 5, 5 plus 2, 7, 7 plus 2, 9, and then the matches. This is one possibility. What we can do is we can change the position of this amine group. Now this is at the first position. We can take this amine group to the second position so that this is second isomer. What you can do, what is the third option? You can't put NH2 here, then again it is equivalent to first position. So you can keep NH here and here, and you can attach different groups here. So we can attach CH3 here and CH2, CH3 here. We are bringing the nitrogen to the center. Okay, so this is one more possibility. So this is a secondary amine. The other possibility is what you can do is CH3, N, CH3, and CH3. This is the fourth possibility which you have. So these two here, it is a primary amine, and here you have secondary and the tertiary amine. So the number of possible isomers can be maximum, it's 4. So the correct answer would be option C. diethyl ether and the methyl propyl ether are. So what exactly is chain isomers? Let's see the options first. Chain isomers in the sense, in the main chain, you should have different number of carbon atoms. Functional group isomers in the sense, they should have different functional group. But here, both the cases, ether is the functional group. So the option B is ruled out. And the metamers and the enantiomers. So let's see with option A, C, and the D. Diethyl ether, that's O in the center, that's ether group, and C2H5, that's a ethyl group. And on the other side, we also have C2H5. So this is diethyl ether. And the methyl propyl ether is CH3. This is a methyl group. And on the other side, you have C3H7. This is methyl propyl ether. Now, if you consider the number of carbon atoms in the main chain, this 2 plus 2, there are 4. Or you can even take one of the main chain, and then here there are 3 plus 1. So this can't be the chain isomers because the number of carbon atoms in the main chain remains the same. So metamers. What exactly is metamer? These are the isomers, structural isomers, which have different groups on either sides of the functional group. So this is considered as the functional group. Here you have one side C2H5, here you have C2H5. And here this is a functional group. And what you have here is CH3 on one side and C3H7 on the other side. So these two compounds differ in the groups which are adjacent to the functional group, so they can be metamers. And the enantiomerism is not possible because the carbon is attached to everywhere. There is no chiral center and the carbon is attached to the similar groups. So the correct answer would be option C. Let's go to the next question then. Which method is used for the separation of a mixture of methanol and acetone? So we know that acetone is a substance which is used in the nail polish remover. So you know that when you keep it open, it evaporates. So acetone has a low boiling point, right? In the methanol, this also has a low boiling point. Now, if you consider the boiling point, this is around something around 60 and this is around 65. And the boiling point difference, roughly, it can be up to 8 or 10. The difference in the boiling point can be maximum up to 10. So when the boiling point difference is very small, you can't go for the regular distillation. That's a simple distillation where you need, if you have to do the simple distillation, then the boiling point should be the difference in the boiling point should be high, so that what you're going to do, you're going to boil the substances or the mixture. One is going to evaporate, the other one is going to remain in the round bottom flask. So this is not possible. And both are liquids. The sublimation is from directly solid to gaseous phase, so this is not possible. And the steam distillation, you can't do that here because both of them have the low boiling point, which is in the same range. And the fractional distillation is the one which you're going to do for the substances which have their boiling point difference very low. So what happens in this particular case is you're going to take the mixture of methanol and the acetone, and there is a fractional column which is attached to the round bottom flask. And when you boil them, the one with the lower boiling point boils first, and it gets collected in the column, and then it cools down, and then the other one which has a little higher boiling point is going to evaporate. So this is a fractional distillation. When the boiling point difference is small, you should go for the fractional distillation. So the correct answer would be option D. So suitable solvent in crystallization means, so here the crystallization refers to, it's a separation technique. You can get the pure crystals out of it. So this is very important method of purification or the separation of the crystals. And what you're going to do here, and what is the procedure, and what is the correct option? Suitable solvent, the question is suitable solvent, regarding the suitable solvent. So what are the options given? Cheap and easily available solvent, that's the first option. A solvent in which the substance is insoluble but impurities are soluble, or the substance can be dissolved at low temperature, or the substance is less soluble at room temperature and soluble at higher temperature. Basically, when you select the solvent in any separation method, you are going for the cheap and the easily available solvent, and that should be non-toxic as well. But It's not the only criteria when you are going to select the solvent. And what happens during the crystallization is you are going to dissolve the substance, or if it has the impurities, you are going to dissolve the substance in a solvent, and solvent is selected. The solvent can be water, methanol, etc. But the solvent is generally selected in such a way that the substance is less soluble at room temperature or in the cold conditions. Okay, so the substance is soluble at low temperatures, and then after this you are going to heat the solution, so the substance is going to be more soluble at higher temperature. After this, what you are going to do is, once the salt gets completely dissolved, or the substance gets completely dissolved, you are going to cool it down. When you cool it down, again the substance becomes less soluble so that it can crystallize out. So the correct option would be solvent is less soluble at room temperature but soluble at higher temperature. Hi, yes, I have received a message. Ma'am, please NEET level questions discuss kar lo. So whatever I have selected, the questions are basically of NEET level. Thank you, Nivedita, for responding. Which solution is used for the separation of a mixture of phenol and aromatic carboxylic acid? So let's write the structure of phenol first. This is phenol and this is a carboxylic acid, aromatic carboxylic acid. Yeah, we have the tips now. We definitely have the tips. Watch until I finish this chapter. Definitely will give you the tips. So when you see this phenol and the carboxylic acid, both are acidic in nature. But phenol is weakly acidic compared to the aromatic carboxylic acid. So if you are going to treat them with sodium hydroxide, both of them are going to react. This also reacts, this also reacts. Where the hydrogen, that's a proton, gets replaced by Na in both the cases. So you can't separate a mixture of phenol and the aromatic carboxylic acid. So using the sodium hydroxide and sodium bicarbonate or sodium hydrogen carbonate, if you're going to take it, what happens here is sodium hydroxide, sodium hydrogen carbonate, I mean to say, this is a weak base. So this can abstract a proton from the comparatively stronger acid, that is the aromatic carboxylic acid, but this is not strong enough to remove the proton, abstract the proton from less acidic phenol. So only this is going to react and this is going to produce the carbon dioxide bubbles. So the H which is there here, that gets replaced by sodium and you're going to get the carbon dioxide which comes out on the form of bubbles, whereas the phenol is not going to react. So the correct answer would be NaHCO3, which can separate or distinguish between the phenol and the aromatic carboxylic acid. Even the calcium oxide, you can take the mixture of sodium hydroxide and the calcium oxide, which is called as soda lime, using which you can, or both the substances, that's a phenol and the carboxylic acid, both of them can react with that. So the one which can distinguish is option B. Yeah, the molecular formula of the compound, that's a diphenyl methane, is C13H12. How many structural isomers are possible when one of the hydrogen is replaced by the chlorine atom? So when you say you're going to replace the hydrogen atoms, there are many possibilities. I'm rewriting the structure here. If you're watching this, please comment down the right answers. So where are hydrogens? Here there is one hydrogen. Then here there is hydrogen in the second position. Then after that, here you have hydrogens. Then here you have hydrogens. And this position are equivalent. This position and this position are equivalent. And similarly here, if you replace this hydrogen or these hydrogens, all are one and the same. So we can take different positions. One is here, the second one is here, and the third one is here. Rest all are equivalent in this ring as well. So from these 3 hydrogen replacements, you can get 3 isomers. And the other option would be you are allowed to just interchange or replace 1 hydrogen. So if you can replace 1 hydrogen from here, you can get 1 more. So the possible structures are 1, 2, 3, and 4. So the correct answer would be option D. Let's move to the next question. Hope I cleared the doubt. The number of possible optical isomers and the chiral centers for aldopentose. So whenever you say aldopentose, what you can expect? So you have 5 carbon atoms. That's why that's what the name pentose stands for. And although they have given, so one must be aldehyde group. The functional group should be aldehyde. And we can write any other structures here. And any other group. Say I'm going to just put OH here, and hydrogens on the other side, just to satisfy the valency. And here I'm going to put a random group. Now what happens? Here the bond is C double bond OH. The carbon is attached to only 3 different groups, so this can't be a chiral center. If you consider this carbon, this is attached to 1, 2, 3, 4 different groups, so this can be a chiral center. If you consider the next carbon, this is also attached to 4 different groups, so this also can be a chiral center. And if you're going to consider this carbon, this is also attached to 3 different groups, so it can be a chiral center. But this carbon is attached to 2 hydrogens here, so this can't be a chiral center. So the possible chiral centers are 3 chiral centers. So when you say it is 3, I'm going for the second option. Don't get confused with the first one. I'm not referring to the optical isomers. I'm just referring to the chiral centers. That would be 3. When you say 3, what happens? It should be option A or B or C or D, where you have 3 as a second one. That's present only in the option C. Okay, so if there are 3 chiral centers, then the number of possible isomers would be, it's usually 2 to the power n. So where n refers to the chiral centers, when you are going to apply that 2 to the power 3, that's equal to 8. So 8 optical isomers are possible and there are 3 chiral centers. The next question, the optically active tartaric acid is named as D plus tartaric acid because it has. So basically this D and the capital D, I'm referring to the capital D, and L, these come from glyceraldehyde. If you know this, immediately you can say option C. But if you don't know this, let me explain. Here, in case of glyceraldehyde, if you take this compound, this is attached to 2 different groups, and you are going to take the last chiral center, that's the bottommost. Decide where the OH is. This is on the right hand side. This refers to dexter, that's D. And if the compound or any other compound, say the tartaric acid, has a OH group on the right side, the last chiral center, the right side, then it is named as D. So this D is from the glyceraldehyde, and this plus and the minus symbols which are present here, they refer to, or small d and L, they can be denoted by this way also, they refer to their optical rotation. The one which is with the plus symbol that can rotate the plane polarized light to right, and the negative one or the minus refers to the rotation of the plane polarized substance, plane polarized light by the substance to the left side. So you can easily remove. L stands for left. Okay, so the correct answer would be option C, optical rotation, and it is derived from D plus glyceraldehyde. So our next question is here. Which of the following compound does not show the position isomerism? So if it has to show the position isomerism, the position of either functional group or the double bond, or the functional group in the sense double bond. It can be a functional group or the substituent. That should be different. So here, if you take the butene, I'm not satisfying the valency, just putting the carbon atoms and the functional group or the position. And this you can even shift to here. So you can get to 1 butene as well as 2 butene, right? In the butanol, when you say butanol, there should be 4 carbon atoms and the CHO group. Al refers to aldehyde, but always aldehydes come at the end. This is the formula of aldehyde, C double bond HO. So this can't come in between. If it comes in between, then it is called as ketone. So either you have to put this side or this side. Both are one and the same because you are going to name the number from the functional group. So this can't have the position isomerism. If you take the third option, that's a butanamine. There are 4 carbon atoms. Basically, when you say but and 1, 2, 3, 4, you can put NH2 here at the first position, or even you can put NH2 here. That is going to give the different position for the functional group. So this can show the position isomerism. And just like butene, which has the 4 number of carbon atoms, that can have a triple bond here, that can have the triple bond here as well. So the correct answer, the one which can't show the position isomerism, is option B. We have the assertion here, in styrene, geometrical isomerism is not observed, and the reason is all the atoms in styrene molecule are in one plane. So when you say styrene, you have to write the structure to get this. So this is a structure of styrene. So here there is a double bond outside. Geometrical isomerism is not observed. The condition for geometrical isomerism is there should be a double bond, and also there should be different groups attached to that. So if you see here, this carbon is attached to 2 groups. That's hydrogen and the hydrogen. And if you consider this carbon, this is attached to a ring here, and the other one will be hydrogen. So now if you see, this group is different from hydrogen, which is attached to the same one. Here for this carbon, both atoms which are attached are hydrogens. So what happens? It can't show the geometrical isomerism. If these were different, then it can show the geometrical isomerism. Now it can't show the geometrical isomerism. So the assertion is correct because it can't show the geometrical isomerism. And all the atoms in the styrene molecule are in one plane because all the carbon atoms which are here, all of them are sp2 hybridized. That means doubly bonded. When you have sp2 hybridized carbon, what happens is, we know that they lie in the same plane. That's a trigonal planar. That's how we define the structure of sp2 hybridized carbon. So they lie in the same plane. So the reason is also correct. But styrene, for not showing the geometrical isomerism, the correct option, the correct answer would be there are similar groups attached to the carbon. So this can't be the right answer. So both assertion E and R are correct, but reason R is not the correct explanation for the assertion. That would be the right answer. So we have the next question here. Assertion A, fumaric acid has lower melting point than the malic acid, and the molecules of fumaric acid are more symmetric and can arrange more closely in the crystal structure. Let's write the structure of fumaric acid and the malic acid first. So C over H and the H here, H and the C over H. This is a dioic acid with a double bond. So the first one is a trans form. You can see that. Trans in the sense COH groups lie on the opposite sides. And this is a cis form where the functional group, these are the main principal functional group, these are lie on the same side. So this is called as a cis isomer. So when you say cis and the trans, what happens is here, because of its geometry, because of the symmetry, this is going to arranged very closely. The packing is very efficient. When the packing is efficient, what happens is you need more energy to convert it into, both of them are white solids, you have to remember that. If you have to melt them, you have to supply more heat. That means the melting point is high. So usually the organic compounds will have the melting point in the range around 150. So this has around 150, 135 degrees Celsius, and this has around 280 degrees Celsius. So the boiling point is very high, or the melting point is, I'm sorry, melting point is very high because the particles, because of its structure, they are tightly packed and they can arrange more closely in the crystal structure. Option, that's a reason is correct, but the fumaric acid has higher melting point than the malic acid. So assertion is wrong, but the reason is correct. So the correct answer would be option D. So we have the next question here. The enolic form of acetone is going to contain enol and the ketone. So this refers to the keto-enol tautomerism. Let's write the structure. We are much familiar with the acetone, so I'm going to write it first. This is acetone. And the enol form is when one of the hydrogen shifts here, then the double bond comes here. So I can write it as COH, double bond, CH2. I'm writing this way to make it easier. So the C is here, hydrogen is here, hydrogen is here, hydrogen is here. So this is a ketone. C double bond O is a functional group is called as ketone. If you take this one, this is ol, alcohol, and this is ene. Together, it is called as enol form. Now, if you take this compound, you are asked to find out the number of sigma, pi bond, and the lone pair of electrons in the enol form, not in the ketone form. So read the question properly and then answer. So here, one lone pair of electron is on oxygen, and the second lone pair of electron is also on oxygen. Because of that, you can have two lone pair of electrons. So option A, B, C can be correct. D is ruled out. And there is only one pi bond. So option B is ruled out. Option A and C are remaining. Let's see the number of sigma bonds. So this is one sigma. This is second sigma. And this one here down, that's the third sigma. And this is the fourth sigma. And between O and H, you have the fifth sigma. And this is a sixth one. Right? So 1, 2, 3, 4, 5, 6, 7, 8, and ninth one. Here we have the ninth one. So that the option will be 9 sigma bonds, 1 pi bond, and 2 lone pair of electrons. That's option A would be the right answer. The next question is, which statement about the tautomerism is incorrect? You have to find out the incorrect statement. Read the question properly. Tautomers always exist in equilibrium. That's the first option. Can be separated. Second option, it's a chemical phenomenon which can be catalyzed by acid in the base. Third option, they are optically active. So let's take the previous example itself. So that would be easier. That is a way easier. So this is a keto form and this is an enol form. So when you say keto-enol form, keto and the enol forms are of same compound, which are interconvertible to each other. The same compound which can be interconvertible to keto and enol. So there always exists an equilibrium between them. So option A is correct. And they can be separated. See, the functional group which is present there is different, and they can be separated by any of the physical or the chemical process. For example, you can take the gas layer chromatography to separate them. That's a GLC, and it's a chemical phenomenon. Yes, the bonding has been shifted, so it should be a chemical phenomenon, and which can take place both in the liquid and the gaseous state. This is also right, and can be catalyzed by acid as well as base. So if you have acid as a catalyst, first protonation takes place. If you have base as a catalyst, the deprotonation takes place. So both acid and the base can catalyze this reaction. So all the three options are right. But the tautomers are optically active. You can see here the carbon which is attached here to the functional group that has no 4 different groups. When you don't have 4 different groups around the carbon, or the chiral carbon center is not there in the compound, it cannot be optically active. So the incorrect statement about the tautomerism is option D. How many carbon atoms in the molecule is given are asymmetric? Let's write the structure first. It's quite easy one. So this is the first carbon, this is the second carbon, and this is the third carbon, fourth. So OH and the H, here also OH and the H. I'm randomly putting them because this carbon is attached to one H and to OH and written out to outside. So a carbon which is attached to different groups, say 4 different groups. If you take this, the structure of carboxylic acid would be C double bond OH. And there are bonds like this. So there are 2 doubly bond. There is a double bond. So it is not, this carbon is not attached to 4 different groups. Even the last carbon is not attached to 4 different groups. So this can't be asymmetric. And this carbon is attached to different groups. So COH here, a bulky group here, H and OH here. The same thing holds for this carbon also. So these carbons are attached to 4 different groups. So there should be 4 carbons together, and out of them 2 are asymmetric. Which of the following has least hindered rotation about the C bond? So when you take the compound C and C, ethene has C double bond C, C triple bond C, and hexachloroethane would be like this. I'm not writing the hydrogens here, that you already know, you are experts in that. So least hinder. So which can be rotated easily. You have to rotate it around the bond, which is easier to rotate. And it's just like you and your friend. Might have seen in movies, you both have to hold the hands. If you hold one hand of yours with the other person, you can rotate easily. You can rotate this way. But if there is a double bond, if you hold both the hands of your friend, you can't rotate yourself unless you leave hand and then join. So that's the same thing which is going to happen in ethene and the acetylene. Here there is a double bond. When you try to rotate, this bond is going to break. So the same case holds with respect to acetylene as well. The bond is going to break when you try to rotate, and this is the cycle, that's a ring molecule. Again, here the bond is going to break if you are going to try to rotate the bonds between 2 carbon atoms. And the correct answer would be ethane, which has the least hindered rotation. You can easily rotate because it is a single bond. So our next question would be, for which of the following parameters the structural isomers C2H5OH and CH3OCH3 would be expected to have the same values, assuming the ideal behavior? So when you say the same values of the boiling point, that's not possible because the functional group, one is having the functional group OH and the other one is having the functional group ether. These are the structural isomers. And what happens is, in case of these 2 compounds, the boiling points can be near to each other, but not the same. The question is, you have to find out the same values. And the second one, vapor pressure. When their boiling point differs, their vapor pressures also differ. The boiling point is directly related to the vapor pressure. Higher is the vapor pressure, lower will be the boiling point. This is very clear from the chapter solutions. So they can't have the vapor pressure at the same temperature, which is same. So this is not also true. And the heat of vaporization. So if you have to vaporize these liquids, what you're going to do? You're going to supply the heat. Since they have different vapor pressures, different boiling points, you need to supply different amount of heat. So even the heat of vaporization will not be the same. We are left with the last option. But how we are going to find out is gaseous densities. We know that for the ideal, they have mentioned the ideal behavior. So when you see gaseous density, we have to go for the gaseous phase where PV is equal to nRT, which is the ideal gas equation. And we know that PV is equal to the number of moles is equal to mass over molar weight. That's MR. times RT. If you are going to rearrange this equation, I'm taking this here. So PMR is equal to mass over volume times RT. So P into MR is equal to mass over volume becomes density into RT. So P over MR, so P times MR divided by RT is going to give you the density. So this is in the gaseous phase. Since MR is same, you're going to consider them under the same pressure and the temperature conditions, and the R, that's a gaseous constant, gas constant, that is same. And the molecular mass, since they are structural isomers, they have the same formula, the molar mass will be same. So they can have the gaseous densities which are same. So the option D would be the right answer. So the correct statement regarding the comparison of staggered and the eclipsed conformations of ethane would be. So what are you going to say about the staggered and the eclipsed conformations here? So we should write the staggered and the eclipsed conformation. This is a staggered conformation where you are going to represent the first carbon here, and it has 3 carbon atoms, 3 hydrogen atoms, and this will be the other carbon atom, which is denoted by a circle. You have hydrogens attached to this here. This is a staggered conformation of ethane. That's CH3, CH3. The front carbon, you are representing it in the form of a dot. And the next one, which you have here, would be the eclipsed form. What happens in the eclipsed form is, I'm going to write the structure first. Hydrogen, 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 and the hydrogen is just behind this. So you can see these hydrogens are lined up here. One hydrogen is just behind the other hydrogen. So these are lined up. Because of this, there is a repulsion, because all the bonds involve electron, and because of the repulsion, there exists a torsional strain. But if you consider the staggered form, they are not lined up, they're away, they are separated. Because of this, this would be more stable. So the eclipsed form is less stable, and the staggered form is more stable. Let's find out the answers. The staggered conformation of ethane is more stable than the eclipsed conformation, because staggered conformation has no torsional strain. So option C would be the right answer. The next question which we have here is, so someone is saying, hi, thank you for watching. 2 possible stereo structures of the given compound which are optically active are called as what? Let me write the structure first. CH3 here, H here, OH, you can place them anyway, C over H. Now let us see what these answers are. What are the options? Diastereomers. Diastereomers refer to the 2 different compounds which are not the mirror images of each other, but they are optically active. So here there is only one chiral center. What you can do is, the other way to write the structure is just interchange the position of OH and H. This is the only option which you have. So if there were 2 chiral centers, then you could write the diastereomers. Now to arrange this in a different pattern, this is the only option available. So these can't be the diastereomers. And the geometrical isomerism refers to if you have the double bond between 2 carbon atoms. There is no double bond found in the compound, so they can't be geometrical isomers. And then the option C would be enantiomers. Enantiomers are the compounds which are the mirror images of each other, but these are non-superimposable. Just like I hold my hand, you can see this hand. If I'm going to place this, if you take these 2 hands, and if I'm going to place it over the mirror image, they are not going to impose over each other, right? So these are non-superimposable, because if you're going to keep just this over this, H will come over OH. So they are not superimposable. So the answer would be enantiomers. Mesomers are the compounds. There might be a plane of symmetry or the center of symmetry, but it is not so in this compound. So the next question which we have, if there is no rotation of plane polarized light by a compound in the specific solvent thought to be chiral, it may mean that. So we are thinking the compound is chiral. But if there is no rotation of the plane polarized light, this seems like it is not going to rotate the plane polarized light. That means it is optically inactive at some time. In a specific solvent, they have mentioned, not everywhere, in a specific solvent. So what is the meaning of this? Options given are the compound is certainly symmetric. So this need not be, because they have mentioned the specific solvent and there is no rotation of the plane polarized light, which is thought to be chiral. So the symmetric is chiral. So this can't be the answer. The compound is certainly a meso. Meso is when, like, I'm going to just explain with an example. You have XYZ attached to this and YXZ attached to this. And then you have a plane. If you're going to fold it over this is going to give you a meso compound. This is again not the option. And there is no compound in the solvent. That is not possible because they have mentioned, right, that there is a compound. So option C cannot be the answer. The compound may be a racemic mixture. Racemic mixture in the sense, if you have a compound like this, for example, C is attached to four different groups, and this is going to rotate the plane polarized light to say right. And if you keep the mirror, you are going to get the mirror image of this one, like this. And now these are non-superimposable. This is going to rotate the plane polarized light to left. And when equal amount of D and L forms, this is a D isomer and this is a L isomer. Whenever you have the equimolar mixture of D and L, the optical rotation which is caused by D is going to be cancelled by the optical rotation which is caused by the L isomer, which is called as a racemic mixture. Due to change in the environment or the temperature or the solvent conditions, the compound may behave as a chiral, but the compound is definitely a chiral substance. So the next question which we have here is, an alkane can show structural isomerism if it is going to have what? How many number of minimum carbon atoms? So to find out the answer for this, we'll start with 1. This can't show the structural isomerism. If you have 2, again, it can't show the structural isomerism. If you have 3, like this, and if you're going to put it here, that's again going to become 3 this way. There is no other way to arrange this 1 or 2 or 3 carbon atoms. But if you have 4 like this, what you can do, this is a straight chain and you can put it down here. So they have mentioned an alkane, so we have put the single bond in between, and 1 carbon can be removed from one end and can be put down here. So these are going to show the chain isomerism, which is a part of structural isomerism. So there should be minimum number of carbon atoms, which is 4. So the next question which we have here is the molecular formula of a saturated compound is C2H4Cl2. The formula permits the existence of 2 what? So the compound, saturated compounds, the meaning of saturated compound is there should be a single bond, C2, H4. So I'm just putting them as a bond, and there are 2 chlorine atoms. Now, functional isomers is one of the options. There is no functional group other than the single bond here, so this can't be the option. Position isomer refers to change in the position of the substituent or the functional group. So this is regarded as a substituent here. And the optical isomerism, the carbon here is attached to similar groups. That's hydrogens are similar. So there is no chiral center. So the compound can't be optical, that can't show the optical isomerism. And the next one is cis trans to show that there should be a double bond, which is not there. They have mentioned that it's a saturated compound, so it can't show the cis trans isomerism. What we can do is here, we can change the position. So one of the hydrogen, we are going to put it here, and the chlorine, we are going to interchange here, so that you are going to get So one would be 1,1-dichloroethane. The second one would be 1,2-dichloroethane. So they can show the position isomers. They are position isomers. The next question which we have here is, in ethane and the cyclohexane, which one of the following pairs of the conformations are more stable? In ethane, if you consider the ethane, there are two forms. One is the staggered. This is the front carbon which we have, and this is the back carbon which we have, and this is a staggered conformation, and the eclipsed is one where you are going to see the hydrogen one behind the other. So this is the second carbon. This is hydrogen is just behind this. If you consider these two forms, we have already discussed this. This is eclipsed. What happens during eclipse? The same thing. One comes in the way of the other. So here, the staggered form, there is no much repulsion between these two because they are not lined up. And this has more stability or more stable compared to the other because of less repulsion between the hydrogens. And there is less torsional strain. And if you're going to consider the cyclohexane, so staggered form is more stable. So where you have the staggered, you have B and C. A and D are ruled out now. Now we are going for the boat and the char form. So this is the char form, and this is a boat form. Say every carbon is going to have two hydrogens here. Let's consider only this. Again, there is a possibility of repulsion over here in the torsional strain. But if you consider here, no, the carbon atoms which are here, there are in the different planes, because of which they are in the different angles, different directions. Because of this, this is the chair form, which is more stable than the boat form. So the correct answer would be the staggered form and the chair conformation. That's option B. Lactic acid shows which type of isomerism. So let's me write the structure of lactic acid first. This is a structure of lactic acid. What happens here is we already discussed about this. Geometrical isomerism can't exist because there is a no double bond. Optical isomerism can be formed because this carbon is attached to 4 different groups. So if you keep a mirror over here, you are going to get the mirror image of that. One would be D, the other one would be L. So this can show the optical isomerism. Tautomerism cannot be possible here because there is a no double bond. Keto enol cannot be observed. And the metamerism, so the number of carbon atoms is just 3, and there can't be different functional groups around the around the carbon or the functional group. There can be different groups around the functional group. So this is not possible. The correct answer would be option C. Which of the following statement is not true about the diastereomers? So when you say the diastereomers, I'm just going to take one example. We'll write the different groups here. So this is X, this is Y, this is Y, this is X. I'm just putting random groups. These two are the chiral centers. And because of the presence of two chiral centers, this the diastereomers is going to be optically active. And if I'm going to write a structure like this, where I'm just keeping this Z in the same place, I'm just going to rearrange this in other form. Okay, so we can randomly interchange this. Y, X, we can interchange this. Now, if you consider these two structures, these are not the mirror images of each other. So they can have the similar chemical properties because the groups which are attached on the functional group, everything is the same. The different physical property can be because of the arrangement of the groups around the chiral carbon atoms. And optically active with same or opposite sign of rotation. You can see in this particular carbon atom, Y is on one side and in the other one, it is on the same side. And this has a plane of symmetry as well. So basically stereomers refer to, these are not mirror images of each other. These are not the enantiomers. Only enantiomers can have the opposite signs of rotation, not the diastereomers. These are nowhere related. So these are optically active with same or opposite sign of rotation. This particular statement is not true. The question is which is not true. The next question which we have here is match column 1 with column 2. So what we are going to do here is we have to match. The options are given on the left hand side. Let's see the functional group here. It's same. So there are different groups. If you observe the molecules clearly, there are CH3, 1 carbon atoms this side. There are 3 carbon atoms this side. ET refers to ethane, ethyl group. So there are 2 carbon atoms here, 2 carbon atoms here. So the same functional group, different groups on either sides of the functional group, that refers to the metamers. So I'm just putting the line over here just to make it clear for you. The option B, you can clearly see here this methyl group is at 1 and 2 positions, whereas here the methyl group is 1, 2, 3, 4, 4th position. The position of the substituent is different. So this can show the position isomerism. So this goes with here. And that's option C. What can be the answer here? This is a double bond and OH. So this is ene and this is ol. And you have ketone group here. This is on. So this can show the keto-enol tautomerism. The compounds have the same formula, but they show the keto-enol, the interconvertible forms of each other. And this one, if you see here, the molecules are interchanged, and this one is a chiral carbon center. Right? So which is attached to 4 different groups. So this can be enantiomer. So if you match this, A goes with R. So you have only A and B and C. Then the B will go with the Q, which you have A and B as the options. And the C is going with the S, which is only option. This one, D is going with P. The last question which we have here is but2-ene exhibits cis-trans isomerism due to. We know that the cis-trans isomerism is observed in case of the compounds which have the double bond. When you say cis-trans isomerism, let's write the structure of but2-ene. But in the sense there should be 4 carbon atoms and H3 here, there is 1 hydrogen here and 1 hydrogen here and H3. So if you consider this carbon and this carbon, which is involved in the double bond 1, 2, 3, 4, what happens here is the carbon number 2 is attached to a double bond. Carbon number 3 is also attached to a double bond. But when you see the double bond, you can't rotate it clearly. Okay, the groups which are attached to 2 and 3rd carbon, they are different. So this can definitely exhibit as cis-trans isomerism. But around this double bond, across this double bond, you can't rotate it unless you break it. So because of the restricted rotation, there is a restricted rotation, not the regular rotation. The restricted rotation around the carbon 2 and carbon 3 is going to make but2-ene exhibit the cis-trans isomerism. So in today's class, we just completed with the isomerism, the important concepts of isomerism, and also the separation techniques. And in the next further classes, we are going to see rest of the chapters, and I'm going to give you the tricks as well, how to eliminate the wrong answer and how to select the correct answer, what are the shortcuts you can see. So if you like this video, please click on the like button and subscribe. Thank you for watching.